It's been very nice to be here for the presentation today. I am Thomas Paulroy, Assistant Professor from the Department of CSE. On this great day of occasion, I am going to present you the topic Asymptotic Notation, which comes under the subject of Design and Analysis of Algorithms, which will be applicable to the Computer Science and Engineering students second years and to Information Technology students too. And the major impact of this topic is mainly used to assess the efficiency of algorithm. See, in the real-time computing scenario, the implementation of software applications is going very vastly. If you want to produce a quality product, the efficiency of product is highly important. So asymptotic notation plays the major role in assessing the efficiency of algorithm, which defines the quality of the algorithm. So asymptotic notation is the major topic today for the discussion. Before dive into this topic, we are supposed to remember some of the basic terminologies. For example, what is meant by algorithm, and what exactly meaning of algorithm analysis, and what is the point of need in analyzing the algorithm, what are all the resources which has been required for analyzing it, what are all the resources to be analyzed, and where exactly it is to be utilized. And later on, after analyzing some of the resources for the algorithm, some of the third attributes also will place in assessing the efficiency of algorithm. For example, best case analysis, worst case analysis, and average case analysis of algorithm. For that, we are supposed to discuss some basic example, how exactly the worst case differs with the best case algorithm. And later on, how to know about the orders of growth measure, which has been mainly used to assess one of the resources. It plays a major role in defining the asymptotic notation. And ends up with what is meant by notation, and what exactly meaning of asymptotic notation, how exactly a mathematical formulation is being defined. Let's see the basic terminologies first. If you want to produce the quality software, algorithm plays a major role. As we know already that algorithm is the step-by-wise instructions or step-by-step or procedural instruction for accomplishing any type of a task. For example, if you are in the industry or in any type of institutions, there might be the need to have the employee paycheck calculations. Or if we are in the educational institution, we are in a position to calculate the students' mark analysis. If you want to progress this kind of activities, algorithm plays the major role. It provides step-by-step unambiguous instructions. Unambiguous in the sense, it has to be represented without confusion. That is, each and every statement has to be stated clearly. For example, algorithm plays an important thing when once after the definition of the problem statement. If you want to design a software for the particular company, first a problem statement will be initiated. Once after the problem statement is initiated, as a software engineer, we are in the position to write the efficient and effective algorithms, which will get stored in your computer system. Later on, by passing the possible input instances, your algorithm is supposed to place the role such that it has to provide a failure-free operation. So algorithm, if you want to define a algorithm is effective, or it has to be qualified one or quantifiable one. See, if you want to produce a quality product, okay, quality plays a major role here. So quality of any software product can be assessed by using the important factor called efficiency. So there are two types of efficiency actually available in the software development. One is time efficiency, other one is the space efficiency. So time efficiency, it signifies how fast your algorithm will be executed. Okay. For example, I wanted to say the real-time scenario. Assume you guys are going and browsing any websites like google.com in a system. Suppose if it takes longer time to load a particular home page, what will be running on our mind? It means the execution of algorithm, if it takes longer time, means definitely all people will get depressed. So execution of any algorithm is supposed to be optimal. It has to be executed fast. So it defines how fast your algorithm runs. Space efficiency, it defines how much memory units will be occupied by the particular algorithm. If you want to execute any algorithm for end users, it has to occupy minimum or optimal amount of memory storage. Next basic term to be remembered is analyzing an algorithm. So analyzing an algorithm is an important research area which is mainly used to analyze the complexity of an algorithm. So there are two types of complexity can be assessed. One is time and space complexity, as we discussed earlier. Okay, so what is a major necessity of algorithm analysis in the sense? Assume you wanted to solve any type of problem. For example, swapping of two numbers. Swapping of two numbers has many type of solution. For example, solution number 1, solution number 2 or solution number 3. Among these three algorithms, as a software engineer, we are supposed to determine which one is the best algorithm. Okay, suppose algorithm 1 may be best or superior to other algorithm in terms of computation time or by memory utilization. So as algorithm analysis is mainly used to assess or identify the best algorithm. So what exactly we are going to analyze using this algorithm analysis in the sense, we are going to determine what is the total running time of algorithm, because in software development time we are supposed to design algorithm, it has to be executed in faster manner. So total running time supposed to be optimal. You have to determine total time consumed by an algorithm, what is the robustness of algorithm, what is the complexity of algorithm, that is what is the time and space consumed by the particular algorithm. These are all the major aims supposed to be analyzed when analyzing an algorithm. So most important resources supposed to be analyzed is time and space complexity, as we discussed before. So what is space complexity? Space complexity signifies amount of memory units needed for an algorithm. For example, if you want to write a routines for the particular program, a program will be comprises of instance variables or constants. So space for the entire algorithm will depends on constant used in the program and instance variable used in the program. That is where we use the formula S equivalent to C plus SP. And there are two types of requirement actually, fixed space requirement and other one is variable space requirement. Variable space requirement in the sense, during the execution time of a program only, the space needed for the particular algorithm will be assessed. That is called dynamism. So there are two kinds of space complexity is also available. And next one is time complexity of an algorithm. So time complexity of algorithm signifies total running time needed for the program execution. With reference to the program, there are two times needed. One is compile time and other running time of algorithm. For example, you just imagine about the scenario of C program. Assume your program is being compiled with system number 1. A program which is being compiled in one machine can be executed in other machines. There is no need of recompilation normally. That is the reason scientists have discovered this issue. The compilation time focus is not being paid for calculating the running time of algorithm. So the major focus is being paid for the running time of an algorithm. So the complexity of the entire algorithm is measured by using these two measures only. One is time complexity and other one is space complexity. So for example, one more measure is there, time complexity. In measuring the running time of algorithm, basic operation count measure is being taken. For example, the system configuration is different in respect to the institution or industry. Assume a program is being executed on one machine. The configuration might be different. It might execute a program number 1 by 10 milliseconds. Suppose if it is an advanced version of configuration, it may execute the same program in 5 milliseconds. Okay, so the difference is there. So execution of time for the same algorithm is different in respect to the configuration of the system. So this measure is being discovered by the scientists. That is the reason for measuring the time complexity of algorithm, all scientists have taken the common measure called running count, the basic operation count. So time complexity is measured by counting the number of times the basic operation is executed. So what is the purpose of this analyzing algorithm finally? So algorithm analysis helps the designer to assess the efficiency of algorithm based on the problem input size. For any problem, there might be the end size of an algorithm. Based on the algorithm problem input size, efficiency of algorithm can be assessed. Suppose if you want to say the algorithm is efficient or quality means it has to utilize the minimum amount of resources, that is time of execution of the program should be faster, that is minimum milliseconds, and other one is a space occupied by the program is also should be optimal. You cannot minimize into much level, only the optimal level can be minimized. By discussing this time and space complexity, apart from the problem input size, the algorithm will depends on some other input also. Okay, because each problem will be defined by problem input size n. The algorithm will not depend not only on the problem input size n, it also depends on some other property. In that situation, as an engineer, we are supposed to distinguish what is worst case complexity, what is average case complexity, what is best case complexity. So these three measures plays a major roles in the asymptotic notations. Okay. So for the best illustration, let us consider the sequential search algorithm. Let us consider the example of sequential search algorithm. So we are supposed to remember what are the measures can be used for this algorithm. So input for this algorithm is an array A 0 to n minus 1 of elements and the search key k. And the output for this algorithm is it returns the position of the element for the successful search. Suppose if there is no element present in an array, it returns minus 1. If not, it returns minus 1 value. Okay, so the basic operation of algorithm is key comparison. Okay, so let us consider the sequential search algorithm. This algorithm works by comparing a search key with the element which is being stored in an array. Assume you have an array of 10 elements. Let us consider only 5 elements first. Its index position varies from 0, 1, 2, 3, 4. Assume you have a data elements 10, 20, 30, 40 and 50 and you wanted to search the data element called 50. Okay, this element works by comparing the search key from the list of n elements sequentially. First 50 will be compared to that of 10, then 20 and 30, 40 and 50. Okay, it moves from the initial position of array to end position of array such that it has to proceed until a element is found. If it return, if there is a successful search, it returns the position of element which has been available. Suppose if it is not available, it returns minus 1. So what is the major focus which has been discussed here is, it leads into there are 3 types of complexity. One is worst case complexity, best case complexity and average case complexity. So this algorithm leads you to have 3 more types of complexity. Okay, one is worst case complexity, best case complexity and average case complexity. Let us see the example again. Assume you have a 5 data elements stored in an array. You have a data elements, you wanted to search key some 50 element. Okay, so this algorithm leads you to have a worst case when there is no matching element, or the first matching element appears to be a last element of a list. We are going to see the example of element only A of 5. The size of an array is only 5. In the practical time of scenario, the size of a data structure will be large. Okay, you just imagine about the execution time of an algorithm. See there, you are going to search the last element 50 here. So it execute n times. If first matching element appears to be the last element of a list. Suppose if you want to search the data element 100, which is not available in an array. Even if the data item is not available, the execution of algorithm takes n times execution. So this leads you to have worst case complexity. So worst case complexity of algorithm is it execute n times. Okay. And next one is best case complexity. So algorithm is said to be best case. When exactly in the sense, if it takes only the few comparison. A data item supposed to be taken within the few comparison of a list, it leads you to have a best comparison. So technically it is being represented by Cn of 1. 1 in the sense it doesn't meaning that it takes only one comparison. It takes only few comparison. Within a few comparison of a list, you will have the successful search. And next one is average case analysis. Average case is nothing but the probability of a successful search which lies between best and worst case scenario. So by seeing these three cases of complexity in a real-time computing scenario, worst case complexity of algorithm is being given a more focus. The reason is on worst case only you can determine how much maximum time the algorithm takes for its execution. So best case complexity many times it is not considered, but if it is known for the particular task, it can be used for the improvement of accuracy of an algorithm. Okay, so after analyzing algorithm, we are supposed to remember some of the walkthroughs maximum to be considered for the algorithm analysis. Number one is you are in a position to consider what is the problem input size. So running time of an algorithm is mainly concentrated based on the problem input size n. As I said before here in the example, it depends on the problem input size n here. It is 5. N equal to 5. First it has to be carried out based on the problem input size 1. And next one is units for measuring the running time of an algorithm. Running time contributes the execution time of an algorithm. Okay, as I said before, running time of algorithm is measured by the basic operation count. It doesn't measure with the system speed or the compiler used for the program implementation, because for each and every system configuration it gets different. In order to avoid such scenario, people have identified a common measure called basic operation count. Based on this basic operation count, you can determine what is the total running time of an algorithm. Basic operation is nothing but important operation which contributes the execution of an algorithm. And the next one is orders of growth measure. This is the major measure which can be applied to the algorithms or a function to assess the running time of an algorithm. For example, consider you have two problems or algorithms, you can say algorithm A and B. So there are algorithm A and B for solving the same problem. On particular situation, you cannot say algorithm A is superior to algorithm B. Based on the number of input instances passes to the particular algorithm, one algorithm may be superior to other. So orders of growth is nothing but a measure which is mainly applicable to either a function or algorithm to assess the efficiency or the growth of an algorithm for the different input instances. Okay, so it is mainly used to assess the algorithm efficiency. So next one is the notations. We are moving into the topic now. Notation. Notation, as we know already, that it is a symbol which is being highly used in the mathematical expressions to know the growth of a functions. So the growth of a function is being compared to that of growth of algorithms, because all algorithms is being expressed by the mathematical formulation. So notations are highly used in the computational complexity theory to know about the algorithm's growth, to assess the efficiency of algorithm. So based on that, asymptotic notation formulation have been defined. So asymptotic notation means what? It is nothing but a method which is mainly used to assess the efficiency or estimate the efficiency of an algorithm when the algorithm is executed with the larger input instances. With reference to the example we practiced on the system or a board, we used to practice with the smaller set of inputs. For example, k equal to 5, k equal to 10, k equal to 20. but asymptotic notation asks you to execute all algorithms with the larger inputs. So it is nothing but a method which is used to estimate the efficiency of algorithm. Consider you have two algorithms now. We are going to distinguish which one is the best algorithm. So number algorithm 1 is n cube by 2. Algorithm number 2 is 5n square. We are supposed to identify which algorithm is best. Assume I am going to apply n is equivalent to 1. If you are applying n equal to 1, you are getting 5. So minimum value for this case is algorithm 1 leads you to have best algorithm. So algorithm 1 is best. Suppose if you are applying n is equivalent to 5. So almost it is equal. Suppose you are applying n equivalent to 10. You are getting 500. Here also it is 500. It is equal. If you are applying n is equivalent to so algorithm 2 is best. See there, from this equation one can identify that for smaller set of input values algorithm 1 maybe leads to have best algorithm, whereas by applying the larger set of values algorithm 2 maybe leads to superior when compared to algorithm 1. So asymptotic notation mainly used to assess the efficiency of the best algorithm when the algorithm is executed with the larger set of inputs. This is a major focus for asymptotic notations, to assess the efficiency, to predict the behavior of the algorithm, to compare the growth of algorithms. So to compare, the major necessity of this asymptotic notation is to rank the order of growth of algorithm or to compare the performance among the algorithms. So for that purpose there are three formal notations have been defined. One is big O notation, big omega notation and big theta notation. Technically it is represented as big O, big omega and big theta notations. Okay, so these formal definitions have been defined. The definitions in respect to these three notations have been technically referred as asymptotic growth rate. As I said before, the execution of algorithm is being compared to that of the growth of a functions. Okay, so for that purpose the mathematical formal definitions have been made. So assume you have two non-negative numbers, one is t of n and g of n, and apart from this one more measure have been discussed, one is c of n. It says you about basic operation count. Using these three measures the formal definitions have been made. Let's see one by one. First one is big O notation. We have seen already a three distinguished complexity of algorithms. One is worst case, best case and average case analysis. First one is big O notation. So big O notation is mainly used to assess the worst case behavior of algorithm when the algorithm is executed with the larger input. See, asymptotic notation is mainly used to assess the efficiency of algorithm when it is executed with larger values of n. So big O notation it is mainly used to measure worst case complexity of algorithm if it is executed with the larger values of n. And next one is it is being represented by the big O notation. Okay, during the execution of algorithms it represents the upper bound of resources. How in the sense? So technical synonym is, suppose if you want to say, so we have defined there are two non-negative integers, one is t of n and other one is g of n. If you want to say a function t of n in big O of g of n, there exists a function f of n such that there exists a constant c1 and non-negative integer n naught such that f of n is less than or equal to c into g of n. It defines upper bound of resources for the execution of algorithm for all larger values of n. See there, you have two non-negative integers, that is it is being compared with the algorithm execution. There are two algorithms here. After this break even point, sum of algorithms goes beyond the limit. It represents the upper bound resources. See there, with the constant multiples of C into G of n. This is called big O notation. And best examples for big O notations are n into n minus 1 by 2, big O of n square, and 5n square belongs to big O of n square. So these are all the possible examples which can be assessed to worst case complexity of an algorithm. Let's go for the big omega notation. Next one. So next case is, if you want to assess or describe the best case efficiency of algorithm, one can go for big omega notation. When compared to the big omega notation, it represents the lower bound resources of an algorithm. The same definition, it differs little bit, reverse position. It defines a lower bound resources of algorithm. Suppose if you want to say a function t of n in big omega of g of n, there exists a function f of n and there exists a constant c1 and n0 such that a function f of n will be lower bound of resources with the other function g of n with the constant multiples. Okay, and it has to be executed for larger integer set value. The possible examples of big omega notation is 5n square belongs to big omega of n square, n into n minus 1 by 2 can prove that big omega of n square. So this is the example of graph which falls for the big omega notation to measure the best case efficiency of algorithm. There are two algorithms is being executed. After this non-negative integers, some of the algorithm expression is goes below the bound of resources, lower bound of resources value with the constant multiple c. Next one is big theta notation. As I said before, this is average complexity measure. If you want to measure average complexity of an algorithm, go for big theta notation, which is used to measure the probability of successful search between best case complexity and worst case complexity. So it says there exists a function t of n and g of n. If you want to say t of n in big theta of g of n, so there will be two constants here. One represents the upper bound of resources and other represents the lower bound of resources. Thereby the technical functions can be written as c1 of g of n so there exists two constants here. One is to represent the lower bound of resources and the other one is to represent the upper bound of resources, because it represents the probability of successful search between best and worst case analysis. This is called big theta notations, provided that these complexity will be assessed when it is executed with the larger set of inputs. So after this break even point, there exists two functions, that is t of n and g of n. It represents the probability of successful search between best and worst case complexity. This is called big theta notations. So as a summary, asymptotic notations, it is mainly used to describe the growth of an algorithm with the abstraction that it ignores the smaller inputs, because as I said before, the major constraint is algorithm execution is happening when it is executed with larger set of inputs, and constant factors also will be ignored of, using which the running time of an algorithm can be assessed, growth of algorithm can be assessed, and the efficiency of algorithm can be measured here. So shortly it is represented as big O notation is asymptotic less than value, and big omega is asymptotic greater than, and theta notation is lies between best and worst case complexity. That is the reason it is set it as asymptotic equality. So summary of graph will be, so big O notation, it represents the upper bound of resources, it has the constant multiples of c, and big omega notation says you about lower bound of resources to measure the best case complexity of algorithm, and theta notation says you about probability between best and worst case complexity. Let's see some of the problems related with the asymptotic notation. We are supposed to prove whether it belongs to big O notation, big omega notation or theta notations. So big O notation, which is mainly used to assess worst case complexity of algorithm. As we have seen in the graph, so it defines the upper bound of resources. Only after the non-negative integers, this algorithm leads you to have the worst complexity. It falls with the formulation of T of n is less than or equivalent to C into G of n. It goes for the upper bound of resources. This expression will leads you to have worst case complexity or true only after this non-negative integers. So before this point, there is no need to have a consideration. Doesn't matter. Okay, let's see some of the examples to be solved for worst case complexity. So example of this algorithm is, let's have 5n square, which belongs to big O of n square. You got to prove it whether it belongs to big O of n square. And the next example what we can give is 100n plus 5, whether it belongs to big O of n square. And third one is n into n minus 1 by 2 belongs to big O of n square. We are supposed to say whether it is true or false, whether the given expression falls under the category of big O notation or not. Let's solve this problem one by one. First one, 5n square, we got to prove whether it belongs to big O of n square or not. From this equation, it is identified that, see there, with reference to expression definition, you have two functions, T of n and G of n. So we are supposed to identify what are all the functions available in the given expression. So T of n is 5n square, G of n is n square. Okay, so we are supposed to determine what is n naught, break even point in which the given expression is true, and next one is what is the value of constant. So you are supposed to determine what is the break even point, what is the constant value. Okay, so with reference to the formal definition for worst case complexity, it is T of n is less than or equivalent to C into G of n. Okay, so it can be written as 5n square less than or equivalent to C into G of n. So sorry, C into n square. Okay, so make this expression as 1. You are supposed to determine what is the constant value, what is the n naught value at which the given expression is true, like this. So first let me determine constant value. So you just make this expression into equivalent C equation, thereby divide equation number 1 by n square. It is written as 5 less than or equivalent to C. So therefore value of C will be 5. Now you are supposed to determine what is the break even point. So find n naught. So equation number 1 can be written as 5n square less than or equivalent to 5 into n square. Okay, so now you are supposed to apply various input instances for n such that the given expression is true in this form. T of n is less than or equivalent to C into G of n. See there, apply when n equivalent to 0 to the equation number 1. So it is written as 0 less than or equivalent to 0. It is true. I mean, yeah, it is equal. Now you apply n is equivalent to 1. So value is 5 less than or equivalent to 5. This is also true. Now apply n is equivalent to 2. So you are supposed to determine for first 5 input instances. Okay, among this you are supposed to select the first value. So first n value you just select. How we can select is, first you find out for 5 possible input instances. Among this input it has to be true here. After that select the first n value as the break even point. Therefore it is concluded that the given expression 5n square will falls under the big O of n square when c is equivalent to 5 and break even point n equivalent to 0. So the given expression falls under big O notation. Next let's see the some fractional expressions here. N into n minus 1 by 2, whether it falls under big O notation of n square. Okay, so from this it is identified that T of n is, it has to be translated into T of n less than or equivalent to C into G of n. This is for worst case complexity. So convert this into a form. So n into n minus 1 by 2 less than or equivalent to C into n square. Now you got to find value of constant. So equation number 1. So convert this into C equivalent form. So n square by 2, sorry, n into n minus 1 by 2 n square less than or equivalent to C. Okay. Now apply various input values to n. If n equivalent to 0, C value will leads to infinitive. Don't select this. Suppose if you are applying n equivalent to 1, you are getting C equivalent to 0 here. Apply C equivalent to 2 here. Okay, C equivalent to 2. It means 2 into 1 divided by 2 into 2 square less than or equivalent to C. So 1 by 2, it is less than or equal to C. It is also a positive. N equivalent to 2 here. See there, for the various possible input instances, you cannot select C equivalent to 0 also. You are supposed to get a first positive value. C is equivalent to half. It means you are supposed to select the constant value is the coefficient of higher order n T of n into first positive integer. Therefore the value is 1 by 2. Next we are in a position to determine non-negative integer n naught. So n value, C values we have identified, it is 1 by 2. Since it is fractional value, this 2 value is being modified as fractional representation. So 1 by 2. Now we are supposed to determine what is the value of n naught here. So expression number 1 can be written as 2 less than or equivalent to 1 by 2 into n square. Apply n equivalent to 0 here. So it means you are getting 0 less than or equivalent to 0. It is equal. Yes. Now you are getting, apply n equivalent to 1. You are getting again 0 less than or equivalent to 1 by 2. It is true. You are supposed to proceed up to 5 possible input instances. Suppose if you are applying n equal to on equation number 1. So you are getting less than or equivalent to 2. Yes, it's true. You are getting a consecutive true values here. Thereby you just select the first true value as a non-negative integer. So therefore the given expression n into n minus 1 by 2 will falls into big O of n square when C equivalent to half and n naught is equivalent to 0. So the given expression will leads you to have worst case complexity when C is equivalent to half and n naught equivalent to 0. So these could be the possible examples for measuring the worst case complexity of an algorithm. Let's go for the big omega notation. Next one is problems on big omega notation. With reference to the technical definition, it is mainly used to assess the best case complexity of algorithm. So the formulation is T of n is greater than or equivalent to C into G of n. This equation is supposed to be keep in mind. So the examples for this big omega notation is, you got to prove that, show that the following are true or false. We are supposed to prove whether the expressions falls under the category of big omega notations or not. Let's see the solutions in respect to the big omega notation. Expression number 1, n square plus 10n n square. With reference to equation, it is identified that T of n is n square plus 10n, G of n is n square. So we are supposed to map this into a technical equation. So it is written as n square plus 10n greater than or equivalent to C into n square. This is equation number 1. So we are supposed to determine what is a constant on non-negative integers such that the given equation is true. We are supposed to find out the constant and the break-even point n naught. So first let me determine the constant value. So equation number 1 is supposed to be converted as a C equivalent form. So equation 1 can be rewritten as, you just divide it by n square. The reason is right hand side is reduced here. So it is written as n square plus 10n divided by n square equal to C. You just divide this expression. So apply n equivalent to various input instances. You just apply n equivalent to 0. So constant value will be 0 here. Okay. You just go for the first positive value. So we cannot distinguish 0 as either positive or negative. So you just have a discarded data. Now apply n is equivalent to 1. So thereby you are getting 11 by 1, that is 11 almost. So 11 is greater than or equivalent to C. So you are getting first positive. Therefore the constant for the given expression is, can be written as higher order of T of n plus first positive n value. So higher order n from the T of n is, see there, it is higher order, see there, you are determining it is 1, it is higher. So 1 plus, and this one is 1, therefore constant value is 2. Now equation number, you are supposed to determine break even point n naught. So equation 1 can be rewritten as n square plus 10n greater than or equal to 2n square. Okay, so now we are supposed to find n naught value. Now substitute various input instances to the equation number 2 here. So n is 0 first. So you are getting 0 is greater than or equivalent to 0. It is true, yes. Now you are applying the value to 1 to the equation number 2. So therefore you are getting 11 is greater than or equivalent to 2. Yes, it is true. And you are applying n is equivalent to 2 now. 4 plus 24 is greater than or equivalent to 8. Yes, it is true. So you are supposed to identify the 4 possible input instances. It is supposed to be true always. Has to be. Once if it is true for successful 4 possible input instances, go for first non-negative value. Okay, so this could be selected as a non-negative integer n naught. Therefore, it is concluded that the given expression n square plus 10n will belongs to big omega of n square when C equivalent to 2 and a non-negative integer 0. non-negative integer 0. Hence it is proved when c is equivalent to a non-negative integer 0. Let's see the another example. Let's see the fractional expression now again. N into n minus 1 by 2 will belongs to big omega of n square. Has to prove that. Now it is rewritten as, let's see the second example. So n into n minus 1 by 2 greater than or equal to c into n square. So find c now. This is a fractional expression. The selection of c differs here because it is fractional value. So you just convert this into c equivalent form. So n square by 2n square minus n by 2n square is equal to c. So 1 by 2 minus 1 by 2n c. Now apply the values for n. When n is equivalent to 0, c leads to have infinitive. Don't select this. Now apply n equal to 1, you will have c is equivalent to 1 by 2. Sorry, it is 0. Now apply c equivalent to 2, you are getting c is equivalent to 1 by 2. It is first positive value. You just select based on this input instance, find out the constant value. Therefore, the constant for the given expression is, select the higher order coefficient of higher order from t of n into, since it is a fractional expression, into, you just make into 1 by first positive. This first positive n value. See there, this is the fractional expression. You have to determine the constant value. On applying n is equivalent to, you are getting c equivalent to positive value. So you are selecting n as a first positive value. It has to be substituted here. Since it is fractional, you are making it into 1 by something. So coefficient of higher order from the given expression is 1 by 2 into 1 by, the first positive is 2. Thereby you are getting 1 by 4. Okay. Sorry, it is 1 by 2 plus 1 by 2. So the coefficient of higher order from t of n by 1 by first positive. Therefore, you are getting 1 by 4. 1 by 2 plus 1 by 2. So constant value is c, that is 1 by 4. Now you are supposed to find a non-negative integers. Fine. So c values, it is identified that 1 by 4. Now find a non-negative integer n naught. So therefore equation number 1 can be written as n into n minus 1 by 2 equivalent to 1 by 4 into n square. Apply n from 0 to 5 positive instances. First n is equivalent to 0. You are getting 0 is greater than or equivalent to 0. It is true. Now apply n is equivalent to 1 here. You are applying n equivalent to 1, therefore you are getting 0 is less than equal to, it is 1 here. It is false. Now apply n is equivalent to 2. 1 is greater than or equivalent to 1. It is true now. Now apply n is equivalent to 3. 2 into, sorry, 3 into 2 by 2. So therefore you are getting 3 equivalent to 9 by 4. Yes, it is true. So therefore you are selecting this value alone. So the first non-negative integer is n is equivalent to 2. Therefore the given expression n equivalent n of n minus 1 by 2 will falls under big omega notation of n square when constant equivalent to 1 by 4 and non-negative integer n naught equivalent to 2 here. This is the final conclusion for the given expression. You are supposed to prove that whether this expression falls under big omega notation or not. Hence it is proved here c equivalent to 1 by 4, n naught equivalent to 2 here. So thereby it is concluding we are big omega notation. Let's see some of the examples related with the theta notations. Let's see the example related with theta notation. It is mainly used to analyze the average case analysis, average case complexity of an algorithm. So technically it is represented as, with reference to mathematical notations, C1 g of n f of n less than or equal to C2 g of n. So this is the mathematical formulation for theta notation. Let's solve the problem for n into n minus 1 by 2 of theta of n square, whether it belongs with the theta notations or not. Let's prove that. So with reference to the given formal equation, you just convert this expression into the same equation. So it is identified that this is going to be the t of n and this section is related with the g of n value. So let's convert this into a given definition. So it is written as c1 n square less than or equivalent to n into n minus 1 by 2 less than or equivalent to c2 n square. Okay. This is equation number 1. So as I said before, for big omega and big O notation, you are supposed to find constant 1, constant 2 and non-negative integers. See there, theta notations, you have two constants here. Okay. Let's see one by one. So first you just convert this equation into C equivalent form. So equation number 1 is divided by n square now. So thereby it is written as C1 less than or equivalent to 1 by 2 minus 1 by 2n less than or equivalent to C2. Okay. See there, from this equation you just see this part alone. It resembles the nature of calculation of big O notation. And when you look at this part alone, it resembles the concept of big omega notation. Big omega notation. Let's find out the answer for C1 and C2 individually. Fine. Let's find C2 first. So 1 by 2 minus 1 by 2n less than or equivalent to C2. Apply values for n. So n equivalent to 0 you are applying, C2 is equivalent to infinitive, n is equivalent to 1 you are applying here. Therefore you are getting C2 equivalent to 0. You are supposed to get first positive value. Now you are getting n equivalent to 2. You are getting, and C2 is equivalent to 1 by 2. See, this is first positive value. Okay. So therefore the constant value is 1 by 2. It is concluded that a constant 2 is 1 by 2. Now find C1 value. See there, right hand side part signifies the big O notation. You are supposed to follow the procedure as we discussed in big O notation. Now you are supposed to find out the answer for C1 based on the big omega notation. So C1 less than or equivalent to 1 by 2 minus 1 by 2n. So apply values for n now. When n equivalent to 0, you are getting C1 as infinitive. When n equivalent to 1, you are getting C1 equivalent to 0 again. When n is equivalent to 2, you are getting C1 equivalent to, it is 1 by 4. It is first positive value. Because of n equivalent to 2, you are getting C1 as the first positive value. So based on this instance, you have to find out answer for C1. So therefore C1 is coefficient of higher order in T of n. So coefficient of higher order in T of n is 1 by 2 in plus 1 by the first positive value is 2. Therefore the answer is 1 by 4. So C1 value is 1 by 4. See there, you just remember the formula, a coefficient of higher order in T of n plus 1 by first positive value. First positive value is 2 here. Because of n equivalent to 2, you are getting the first positive. So 1 by 2 plus 1 by 2 equivalent to 1 by 4. So E1 is equal to 1 by 4. So now you have determined that C1 is equivalent to 1 by 2. Sorry, C1 is equal to 1 by 4. C2 is equivalent to 1 by 2. After finding these values, you are supposed to determine n naught now. These values have been calculated. Now you have to calculate n naught. Let's see how to find n naught value. So apply these two values in the equation number 1, thereby you are getting 1 by 4 n square less than or equivalent to n into n minus 1 by 2 less than or equivalent to 1 by 2 n square. Now find n naught by applying various input instances to n starts from 0. Now apply 0. You are getting 0 less than or equivalent to 0 less than or equivalent to 0. Yes, it is true. Everything is equal. Now you are just apply n equivalent to 1 here. So if you apply n equal to 1, you are getting 1 by 4 less than or equivalent to 0 less than or equivalent to, you are getting 1 by 2. It is false. Now n equivalent to 2, you are just apply. When you apply n equal to 1 less than or equivalent to 1, it is 2. Yeah, it is true. Thereby you are selecting n is equivalent to 2. So select n naught as n equivalent to 2. So therefore the given expression n into n minus 1 by 2 will falls under theta of n square when a constant 1 is equivalent to 1 by 4, constant 2 is equivalent to 1 by 2, and n naught is equivalent to 2. So the given expression will false or it is true for theta notation when C1 equal to 1 by 4, C2 equal to 1 by 2 and n naught equivalent to 2. So this could be the example for theta notations. Let's give you the summary that asymptotic notation is mainly used to assess the efficiency of algorithm when the algorithm is executed with the large set of inputs. So there are three notations have been defined formally. One is big omega, big O and big theta notation. So big O notation is asymptotically less value, big omega is asymptotic greater value, big theta notation is the asymptotic equal value. So using which you can assess the efficiency, you can find out the growth of algorithm, and finally you can provide or you can assess the quality of algorithm. If the quality of the algorithm is good, you can able to provide the quality of the products. That's it for the session today. Thank you. Have a good day.